something like this. So imagine we have a transformation defined by these particular functions. We're going to transform the UV coordinates into the XY coordinates. And we're asked to find the image of the starting rectangle in the UV coordinates over here to find out what it looks like, what the image looks like, this region R, and also to verify that it's one-to-one. It's always good to start with two different graphs separately if you're going to do it on paper to remember you're transforming from one space to another. Then draw out the region G. The rectangular region G looks like this inside the UV plane. I'm just going to shade it in roughly. I want to find out what the transformation region of I want to find out what the transformation looks like using the equations. My x coordinate comes from u plus v, and my y coordinate comes from 3v. I happen to notice that these are linear functions. They don't double back, they don't bend in weird ways. It's just a linear term plus a linear term, or 3 times a linear term. I'm going to go ahead and say that the edge boundaries then are going to remain being the edge boundaries of the other region. I'm just going to assume that's true, and it's a good assumption if you are definitely working with linear terms. So my trick is to find an equation for the edges and graph where those are going to be sent to. This top edge here, for example, can be referenced using parameterized curves as being a u as the variable, and the v coordinate is always 2. U goes from 0 to 1. If I plug 2 in for my v into the transformation function, I get the y coordinate should actually be 2 times 3, which is 6, and the x coordinate should be u plus 2, where u goes from 0 to 1. I'm going to go ahead and plot when u equals 0. I have my starting point of the edge, which happens to be 2, 3. When u is equal to 1, I get my x coordinate is 3 and my y coordinate is still 6. As u goes from 0 to 1, I'm going to connect these two dots because only the x coordinate is changing linearly according to this. Thus, we've mapped the top edge, and we do the same things for the rest of the edges. So I've labeled each of my edges. You can see E2 happens to be, or the second edge I'm looking at is over here on the left. I'm not doing this in any particular order, and I'm not being particularly careful about my orientation of these edges because I don't need to know that information to do this problem. So this edge can be described by fixing the u coordinate always equal to 0, and the v coordinate just varies from 0 to 2. I substitute those into my equation, so u is 0, v just stays as v, which gives me this equation, parametric equation, to graph this curve. It's a simple enough one for me to do. I recognize that these are linear equations, so I only have to plot 2 points of this interval and then connect the dots. So when v is 0, I have the origin 0, 0, plot that point. When v is 2, I have 2, 6, which is this point over here. Connect the dots, and I get that edge. Similarly, if I try to work on this edge, edge 3, which is this edge over here, to see where it gets mapped, I go ahead and plug in the coordinates or parametric description of this in terms of v's. Notice u is always equal to 1 on this edge, and v just varies, the height varies. So I plug in 1, v into the above equation. I get the following equation of 1 plus v, 3v. And similarly, this is the description of some sort of line. It's a linear equation, so I just need to find 2 points and plot the points. If I plug in v equal to 0, I have a 1, 0, which is this point over here. And then if I plug in a 2, I have a 3, 6, which is this point over here. And it must connect these two dots, so I get a parallel line to the one on the left. Finally, I work on the final edge, this edge on the bottom where v is always equal to 0. In this case, you have just u varies, but v is 0, and I substitute it in, I get this basically the same expression, u, 0. Once again, it's a linear equation, plug in 2 points. When u is equal to 0, you get the origin. When u equals 1, you get 1, 0, and those are your two dots that you connect. every point inside this region is going to be inside this region here too. There's no exponential expansion that goes beyond or anything like that. So the image of the region R looks like this thing. We are asked to ensure that this function is one-to-one on its interval, and there's a bunch of ways of doing that. Because this defines a system of linear equations, we could use linear algebra tricks to show that it's invertible. Basically, make a matrix, show that matrix has an inverse or its determinant is not equal to 0. Also, you could just choose two unknown points inside of here and try to solve to show that there's a if you set those 2 points inside the image. Also, you can try to solve the equation that any point inside the image has only a single solution from the original equation. That is, you start by saying you don't know if the function is to one-to-one, which means there's some sort of point, pretend like there's some sort of point inside R that could possibly come from 2 different points inside of G. Mathematically, you just write this way, and you let U1, V1, and U2, V2 possibly different points, but they have the same image, so you set the functions equal to each other. You substitute that into your system of equations, which is what I did over here, where I've got U1 plus V1 is my x-coordinate, but also U2 plus V2 is my x-coordinate, the same x-coordinate value, and V1 and V2 are my y-coordinate values. Sorry, 3V1 and equals 3V2, the y-coordinate values are the same. Then you go ahead and try solving each of these equations simultaneously. If you solve the easier of the 2 equations, the bottom one, you get that V1 has to be the same thing as V2. You can then use that fact in the equation above to say that, okay, we have a U1 plus a V1 equals U2 plus a V1. That's because U2 has to be the same thing as V1 from the previous equation. We go ahead and use algebra to solve, subtract the V1 from both sides, and if you do, you get a U1 has to equal a U2. The only way that you can have the same output of these functions is if their inputs are also the same. Hence, it's a one-to-one transformation.